Hello again. Today we're going to be talking about a little bit more about gas laws and leading into stoichiometry. Today we're going to be talking about the four guys gas laws. It's kind of like the four guys pizzas, just a play on words there. So we're going to be talking about the gas laws that have been developed over time, that were developed actually hundreds of years ago, that make sense and actually that we know a lot about, despite the fact that we're not sure. Okay, so let's take a little review step here. So the properties of gases. Only four quantities are needed. Remember, we need the number of moles, we need the temperature in Kelvin, we need the volume of the gas in liters, and we need the pressure, usually in atmospheres, but we can deal with other different units there. So those are the four things that we need to define states of gases. And so those four things are going to play into the four guys gas laws. All right, so the first guy, and it's all experimental. Everything was experimental. So we have a guy named Boyle. And Boyle came along and said, okay, the volume of a confined gas is inversely proportional to the pressure exerted on the gas. Now, the issue with Boyle's Law, though, is all gases are behaving in this manner. But Robert Boyle used this idea of a J tube and set up some ideas in his home. And he made sure that he was looking at the experimental tubes. So this is Boyle and what he looked like, and this was his experiment. So he had a gas on the other side, basically a closed manometer, okay? And then he was looking at what was happening to that gas and what would happen if you had the same amount of gas, but if you increase the pressure, or if you had the same amount of gas, or if you increase the volume, what was happening between those two things. Now that implied that temperature and number of particles, moles, were the same. So we know we were keeping constant temperature and we were keeping constant number of particles the same. So that meant as volume goes up, pressure goes down. As volume goes down, pressure goes up. It's inverse. And so what we start to look at is this idea that PV is equal to this constant K. We can figure that out a little bit more easily. And then we get the relationship that we need to use. And the relationship that I use, yeah. So when we're looking at trying to find what K is, if we can get the slope of the line where we have 1 over P over V, or we do P over 1 over V, either way it works. We're coming up with the same kind of idea, this idea of what happens here. So the easiest way to remember Boyle's Law and to memorize it is P1V1 is equal to P2V2. And you will see all of these gas laws kind of have the same kind of structure. And as long as we're following the structure, we should be okay. Okay, Boyle's Law has been tested over 3 centuries. It only holds true at really low pressures. So once we get to higher pressures, things get to go a little crazy. So we need to make sure that we're thinking about that. So volume and pressure, we can see that has a super inverse relationship there because of that curve that we have, but we can graph it in a different way. If we graph P over 1 over V, we get a straight line reaction there. So I will show you about that in just a second. So sulfur dioxide gas. This is the first problem. So what are we going to do here? Well, we know that the equation is P1V1 is equal to P2V2. And like all good problems that we have with word problems, we have to define some things. So let's start defining. We have sulfur dioxide gas that plays a central role in the formation of acid rain. It's found in the exhaust of automobiles and power plants. So we have, consider a 1.53 liter sample of gaseous SO2. That's what we've got going on here right now. So we've got V1 is equal to 1.53 liters. And to be honest with you, it doesn't matter if you label one V1 or V2, but you need to keep the V's and the P's together that go together. That's the only thing that you have to do. So, and that SO2 is at a pressure of, so that's a P1 pressure of 5.6 times 10 to the third pascals, okay? If the pressure is changed to 1.5 times 10 to the fourth pascals, at a constant temperature, what will be the new volume? So we know V2 is what we're looking for here, and P2 is equal to, oops, let me change that. That's what we're looking for, okay? P2 is 1.5 times 10 to the 4th pascals. So we look at our equation. I'm solving for V2. So to solve for V2, I've got to divide both sides by P2. So V2 is equal to P1 V1 over P2. So I plug and chug. So this is 5.6 times 10 to the 3rd PA times 1.53 liters divided by 1.5 times 10 to the 4th PA. PA cancels out, leaving me with units of liters. That's a good thing. And then we just plug and chug. So this is just now a solution. So we get 0.571 liters. So we increase the pressure quite a bit and decrease the volume. Our answer must still fit with the relationship. As pressure increases, volume decreases. As volume increases, pressure decreases. We've got to make sure that that's still the case. And in this case, it absolutely is. All right, so this next question really requires us to take some information and go somewhere else. So I am going to go ahead and end my show here for a second. I'm going to discard those for a moment, and I'm going to open up Excel. All right, it takes a second to open up Excel. I probably should have opened this up before I started this. All right, so I've got Excel open here. I'm going to go ahead and make it small. I'm going to come back here and I'm going to get this information. So I'm going to come back and get this information. I'm going to copy that and I'm going to paste it right into my Excel spreadsheet. Okay, so there I go. I have all of it pasted into the Excel spreadsheet. It looks like it didn't paste exactly right, but that's okay because I can fix that. I think I can fix that. So I'm going to go 0.13, 172, 0.25, 98.3, 0.3, 74.4, oops, 4, 0.5, and that's 44.5, and 0.75, and that's 29.6, and finally 1 atmosphere is 22.2. Now, I know that I need to make this 1 over V. So what I'm going to do is I'm going to program that. I'm going to say, okay, equals 1 divided by E1, and enter that. And then I'm going to copy that and I'm going to paste it in. Okay, so I've got all of those. So what I need to do is I need to graph P and V1. So I'm going to hold my control key while I do that. And then I'm going to come up here and I am going to insert, a scatter plot. Okay, I'll worry about everything else later. Okay, so now that I've got this done in Excel, what I'm going to do is I'm going to come up here to add a chart element and I'm going to add a trend line. And I want it to be, I want more trend line options because I want to add something else to it. Okay, so I get my trend line options. I want it to be linear, but I also want to display the equation and I want the R value. So you can see I have an R value of 1, which is great because that means it's very linear. But the more important thing here is that I have a value for K, the constant. Okay, I'm trying to make it bigger, but it's not helping me here. It's not letting me do that. So let's see if I can do here. There we go. So we can see that the value of K is 0.0453. That's the constant. And so that is what we were looking for in that problem, to find the slope of the line and account for the apparent trend in the data. So does it closely relate? And the answer is yeah, with an R value of 1, it closely relates. And then the K value is 0.0453, so that's pretty good too. So we've got an answer for that, and we can account for the trend in the data because of that. All right, so let's go back to our, let's go back here. So we counted for the trend in the data because we used the results listed, and we found the Boyles Law constant for NH3 at various pressures. And we know that it has an R value of 1, and that's really, really good. So we're good to go there. So what else do we have? We have another guy who came along and said, okay, I want to know about given quantity of gas at constant pressure. I want to know what happens to volume and temperature. And what it says here is that as temperature increases, volume should increase. And as temperature decreases, volume should decrease. If you think about a balloon, if I blew up a balloon and put that balloon in a pan of hot water, that balloon is going to expand. But if I put that balloon in a pan of ice, an ice bath, it's going to shrink. So we already know this happens. But this is where Kelvin must be used. And Kelvin has to be used because I cannot have a negative volume. So Jacques Charles was a French physicist, and he was the first person to fill a hot air balloon. And he made the first solo ride. So he was a guy who was doing some things because he wanted to go on a ride. All right, so what he basically says is that volume and temperature are directly proportional. And that if I graph volume and temperature, I'm going to get a straight line relationship with these two things. Okay, so we can see that that happens for almost everything here. We've got these things at absolute zero, and we can have different amounts of them at the same pressure, and we can see that they always make a straight line connection with their volume at constant pressure. Okay, and then we get to this moment of absolute zero. So I'm sure that Charles's law was instrumental in trying to figure out absolute zero as well for Lord Kelvin. So we know that V1 over T1 is equal to V2 over T2. Now they give you this other one, V1 T2 is equal to V2 T1. I think that's confusing. I like to keep them all the same. V1 over T1 is equal to V2 over T2. And as long as I understand what the relationship is, I can really understand that. If it's direct, they're going to be divided by each other. If it's indirect, they're going to be multiplied by each other. So just make sure that you're thinking about that. Okay, so this figure shows a plot of volume versus for several gases, and the solid line represents the experimental measurement on the gases. So where it's solid is what he measured, and where it's not solid is what we figured out to absolute temperature. The dashed line represents the extrapolation to the region where the gases would become liquids or solids. Note that the samples of various gases contain different numbers of moles. What is the temperature when the volume extrapolates to zero? And we can see that it's 0 Kelvin. That's absolute zero. Okay, so here's our first problem for Charles' law. So it says a sample of gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.5 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So we know that we're talking about the equation V1 over T1 is equal to V2 over T2. We're comparing these two values. So we have to start looking. Okay, we have a T2. T2 is 15 degrees Celsius, but we have to change that to Kelvin. So 15 degrees Celsius is 288 Kelvin, okay? That's T1. V1 is equal to 2.58 liters. And we're gonna have to do anything with that. We know that the pressure is the same. It's 1 atmosphere and 1 atmosphere, so we don't have to consider pressure. Pressure is constant. But we do know that T2 is 38 degrees Celsius. So we know that that is 311 Kelvin. and we don't know V2. That's what we're looking for. We're looking for V2. So we're solving for V2. So if I rearrange my equation, I can multiply both sides by T2. And I get that V2 is equal to V1 T2 divided by T1. And so then I plug everything in. I've got V1 is 2.58 liters. I've got T2 is 311 Kelvin. It's really important that you use Kelvin here and you don't use Celsius. And then I have 288 Kelvin for T1. And now I just solve it. And when I solve it, I get 2.79 liters. Now think about that for a second. Does that work? As volume went, or as temperature went up, did volume go up? And the answer is yes. I went from 2.58 liters to 2.79 liters. So that's an important thing to make sure that you have the same relationship that you're looking for. Okay, so Charles' law is also seen in this whole idea of balloons. And this is what I was talking about before. If I put two balloons with the same amount of stuff at the same pressure into different temperatures of water, I will see that the kinetic energy of the first gas in the ice water is going to be lower than the kinetic energy that is in the boiling water. And I'm going to see that the expansion of the balloon gets greater because the balloon is rubber. And so it expands. As things get greater volume, it will expand until it can no longer expand it, and then it will break. So the breaking point of the material is at the point at which we can no longer expand or contract. Okay, and you've seen balloons that have been cold and they get shrivelly, and that's because the material is still being affected by the gas inside, but it's been stretched out. So we kind of see some differences here. So this is the idea, and if you can think about this balloon concept, I think that Charles' law will be really, really simple for you. Okay, the next guy is a guy that we don't mention very often. We don't mention this guy's name is Gay-Lussac. Okay, and Gay-Lussac was basically talking about some other ideas. So Gay-Lussac has two kind of ideas that he was playing with. The first one leads us into another one of the guy's laws, which we'll talk about in just a few minutes. Okay, so combined volumes. When gases react together to form other gases, then all volumes that are measured at the same temperature and pressure, there's a ratio between the volumes of the reactant gases and the gaseous product that can be expressed in simple whole numbers. This was the beginning of this idea of molar relationships found in chemical reactions. So Gay-Lussac was really kind of playing with this idea of chemical reactions happen in very, very specific ratios. So, and he was another French guy, okay? Now, the second idea that he had was that temperature of a confined gas is directly proportional to the pressure exerted on the gas. But volume has to remain constant. So he had to have a constant container that would never change volume. And he was looking at it from a different perspective. So Joseph Gay-Lussac, probably Gay-Lussac, who knows, was a French chemistry person and a contemporary of Charles. So they were kind of working together at the same time. He was right before Charles. They were working through some of this stuff at the same time. So he studied pressure-temperature relationships using the similar setup as Charles, except his device had a fixed volume. So instead of being like a balloon that had an unfixed volume, he had something that was a fixed volume. So that was the biggest difference between Gay-Lussac and Charles. They were kind of on the same path, but Charles was keeping pressure constant, whereas Gay-Lussac was keeping volume constant. All right, so, and this is where we get this idea of pressure. All right, so the next guy is called Avogadro. This is Amedeo Avogadro, and you know Avogadro because you've heard him. So basically he's saying equal volumes of gases under the same conditions of temperature and pressure contain equal numbers of molecules. He's talking about moles. Equal numbers of molecules would be equal numbers of moles. So he was the guy who began to think about this idea of moles. And he was using a paper published by Gay-Lussac when he theorized his hypothesis. He started thinking about what Gay-Lussac was thinking about in the very beginning of this molar relationship. And he said, okay, hang on. There's some things happening here that I think I understand. And so he, defining particles, we didn't know about an atom. So everything was relatively new at this time. And so when he published his paper, the idea of an atom had just come out like 5 years before. So it was still kind of something that they were trying to figure out. And so this hadn't been decided and hadn't been solidified yet, but it's given to Avogadro as his theory and his hypothesis. So if I increase the amount of gas, it increases the volume. So basically we're saying that if we have the same amount of gas, it should have the same volume at the same temperature and pressure. That's what he's saying. So he's relating number of moles to volume of gas. And this is actually where we get the constant that we see used in the molar relationships. This idea that 22.4 liters is equal to 1 mole of any gas at STP. We know what the P is. The P is 1 atmosphere. Okay, but the T is 25 degrees Celsius or 298 Kelvin. Okay. So it's really important to understand that this is where this came from. So Avogadro was talking about an idea that he hadn't quite solidified, but that he had a lot of pieces for, which is why he's given credit for Avogadro's law and Avogadro's number. Okay. So he basically said that N1 over V1 is equal to N2 over V2 because he basically said that the number of moles is directly proportional to the volume that that gas should occupy at constant temperature and pressure. And that's called Avogadro's law. So here we go, Avogadro's law. I know we didn't do a Gay-Lussac problem, but that's okay. I think you got it. Okay, suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all of this O2 were converted to ozone at the same temperature and pressure, what would be the volume of the ozone? Okay, so we have a lot of stuff going on here, so let's start writing it down. We have V1. V1 is equal to 12.2 liters, and that is O2. And we know that N1 is equal to 0.50 moles of O2. Okay, we want to know what V2 is. That's what we're looking for, and that is liters of O3. So we need N2 to get there. Yeah, we have to calculate that. So what we have to do is very simple, right? We know there's a reaction going on here. We know that O2 gas is combining to form O3 gas. This is what we know is happening. Well, if that reaction's happening, then we can balance that equation and we can figure out how many moles of O3 are produced if half a mole of O2 is there. So we start looking at, we've got 2 O's here, 3 O's there. Well, I need 3 O2s here. I need 2 O3s here. So that means I have 0.50 moles of O2. I've got to figure out the moles of O3. So I've got 3 moles of O2 to 2 moles of O3, which gives me 0.33 moles of O3. So I know 0.33 moles of O3. Now I can go back to the idea of N1 V1 is equal to N2 V2. These are just proportions like you used to do. So I'm looking for V2. So I've got to multiply V2 by both sides. Okay, V2, I'm sorry. Okay, multiply V2 by both sides. V2 cancels out. So then I've got to take N1 V1 away here. So I've got to figure that out. So V2 is equal to N2 V1 over N1. I had to rearrange that. So here we go. N2 is 0.33 moles. Okay. V1 is 12.2 liters. and N1 is 0.50 moles. So moles are going to cancel out, and I'm going to get an answer of 8.1 liters, 1 liters of O3. Now, does that make sense? Think about it. It's directly proportional. So what happened to the number of moles of substance? It went down. It went from 0.5 to 0.33. So the volume of the gas should go down as well. Did it go down? It went from 12.2 to 8.1. So always make sure you check your answers, because typically speaking, you're going to be able to get to a different location if you do that. Okay, so combined gas law. Here we go, combined gas law. This is not very hard. In fact, combined gas law is basically taking all of the laws and throwing them together except for Avogadros. Avogadros is the only law that we keep out of here. So we've got Charles, we've got Boyles, we've got Gay-Lussac. And so basically we just throw them all in together. So P1V1 over T1 is equal to P2V2 over T2. And this actually helps me remember the other ones too, to be honest with you. If I keep pressure constant, then I've got V1 over T1. If I keep volume constant, then I've got P1 over T1. If I keep temperature constant, then I've got P1V1. So I find that memorizing this law helps me remember all of the laws. So just make sure that you've got this idea that we can use all of it together. We can use all of it together. And this is a way to start thinking about the problems from a different perspective. So you can look at it from the perspective of, which law is it? You can look at it from the perspective of, can I use all of them? But if you can remember P1V1 over T1 is equal to P2V2 over T2, you can remember that order, you've got gas laws and the four guys laws pretty much tackled, okay?